Hello, welcome back to another episode of Fun with Code. So here we're looking at transformers over 750 volts. So this is the first example. We have a 750 kVA three-phase transformer. It has a 4160 volt primary, a 48277 volt secondary. We're going to use 90-degree rated wire for ampacity, and what that means is this assumes that the equipment is 90-degree rated. Now at this point I just want to say that, or to recall that the 75-degree column in the codebook pretty much rules the roost. We can make the codebook always assumes that the equipment is not marked. That will always give us the higher standard. So I just chose 90 degrees, that the equipment is not marked for 90 degrees, just to give the lesson a little flavor instead of always having equipment not marked. So this is just playing with the numbers a little bit in the code book for the sake of changing things up. Always refer to the manufacturer and find out what the equipment is marked for. So here we're going to install a primary overcurrent protection. We're going to use fuses. We're going to parallel the secondary conductors by 4. The wire itself is 5 kV rated copper. So 5 kV meaning the insulation rating. But the voltage being applied is still 4160. We're going to apply 26250 subrule 2 and 26256 subrule 4 for the overcurrent protection in the wire. So just as we've done in first level, the system is the same. We're just changing a couple elements of the calculation here. So the primary, we take 750,000 volt amps, and that's what, right, kVA. So 750,000 volt amps divided by 4160 times the square root of 3. Because we're dealing with three-phase, we have to apply the square root of 3. So we end up with, on the primary, 104 amps. On the secondary, we're going to do the same thing, 750,000 volt amps divided by 480 times the square root of 3 gives us 902 amps on the secondary. Now always remember, most of our code calculations are all PEI based, right? Power equals voltage times current. That's what we've been doing the whole time. That's what you will always do when we're dealing with code, and this is regulated under 8100. And when we look at the language of 8100, that's exactly what it's telling you. When we're calculating for currents on loads expressed in watts, we're going to apply certain voltages. So always remember that. So we're looking at the primary overcurrent protection in wire, 26250 subrule 1A. We're going to take it at 150%. So we're going to take 104 amps times 1.5 gives us 156 amps. Now notice here, okay, we're dealing with the overcurrent. So when we're dealing with overcurrents, we're typically dealing with the language of maximum. However, 26250 subrule 2 allows us to increase the size. So we'll go to 175. 26256 subrule 4 here. So we have, we're going to use 26256 subrule 4. We're going to use 175 amps here, and then in this portion we're going to apply the turn ratio to calculate for our secondary current. Because we're over 125% here, in first level we dealt with 125% on the primary, 125 on the secondary. Here, because we're at 100 or we're over 125, we're going to use this value. So we have our overcurrent protection, 175. We're going to size this accordingly, and we end up here with a number 2 watt. For the secondary wire, we're going to take the 175 amps that we've chosen for our overcurrent device, and we're just simply applying the turn ratio of the transformer. So we have the 175 amps times the turn ratio, and again this is in line with how we've calculated in the past when we had test 1 and we did the turn ratio calculations. So 175 amps times the turn ratio, we're looking at 1516 amps on the secondary. So we're going to parallel the secondary, and what we're looking at here is 12108 subrule 1A through F deals with the specifics of installing parallel conductors. So we're taking 1,516 amps, we're dividing it by 4 because we are paralleling by 4. So we end up with 379 amps, and that's going to be the value for one of the conductor, one of the 4 conductors. So we go over to table 2 and we size our conductor according to the 379 amps. So 379 amps gives us a 400 MCM, and it's going to be 4 per phase. So what that means is we're going to have 4 400 MCMs for the A phase, 4 400 MCMs for the B phase, and 4 400 MCMs for the C phase and the parallels. So I just want to make note here, when we look at paralleling conductors, in the case of these, there are different ways to apply the parallels, but the way I've set them up in these calculations is we calculate for the current, we apply the parallel, and then we come into sizing the conductor. So it's important, this is where I get problems with students in this section here, is applying 12108. Where do we apply the parallel? And basically in these calculations and previous calculations, we always apply the parallel before sizing the conductor. So that's just the way these exercises have been designed, and so that's what you're looking for. So just to recap, we're taking here again, we're calculating for the primary overcurrent protection and wire. Notice that the secondary, there is no overcurrent protection on the secondary in this case. So another thing to be aware of, and where I have issues with students, is sometimes a student will stick some overcurrent protection in the secondary. But notice this first part of the calculation is the primary overcurrent protection and wire, so the primary OCP and the primary wire. That's what's going on here. Notice there's more calculations going on here. So, and again, we're taking it at 150% according to the rule. We end up with this value, and 26250 is dealing with our overcurrent, right? This is not for wire. So the 156, we apply it into 14104, and 26250 subrule 2 is allowing us to go up to the next standard size. So we've been dealing with overcurrent devices using the languages of maximum. Typically we would go down, this would be a maximum, we would go down to the next breaker size, not up. In this case, though, we're going to apply this rule where it's allowing us to go to the next size overcurrent device, which is also stated under 14104. We deal with the 175. So when we size our conductor, because we're using a 175 amp overcurrent device, we're going to size our conductor according to the overcurrent device. So because we've gone up, we will size our conductor accordingly, and then they will match. You want the wire and the conductor to be as close as possible. And the secondary wire, we're going to look at the current that we've chosen for our primary. We've sized the wire and overcurrent according to the 175, and we're just applying the turn ratio of the transformer for finding the secondary current. So we end up with 1,516 amps. Because we are paralleling times 4, we're going to divide this number by 4. That's 379 amps, and that represents one of the 400 MCM conductors. And then so for table 2, we're going to find that 400 MCM covers the 379 amps, and there will be 4 of those for every phase. So 400 MCMs for A, B, and C phase, and the neutral should it apply. And that is it for transformers over 750 volts. We'll see you in the next episode.